All right, so for this warm-up, we're really kind of focusing on how we can tell the difference, how can we describe given various pieces of information. So when I look at this data here, you see that we have, and just make sure everyone's familiar, this is called our 5-number summary. You know why it's called 5-number summary? Because yeah, there's 5 numbers. It's amazing how that works out, right? Bless you. So would you expect the mean temperature of all students who visited the nurse's office to be higher or lower than the median? Higher? Why? Yes, ma'am. Okay. There's a lot more data points above. Well, you got to be careful the way you say that. Data points is going to be the exact same because median means half of them are above, half of them are below. But there's a greater change or a greater difference. Those are appropriate words. Good. And you can do this a couple of different ways. If I'm looking from the median to quartile 3, that's going to be a difference of, yes? I have an answer. Absolutely. What else do you have to talk about? I understand your point there, but basically we're talking about, like, you have to base it in statistical evidence, and this is the evidence of everybody that comes in. This person was in the nurse's office. I gotcha. I understand. But you got to always work off of the data that you're given. Okay? So from the median to quartile 3, I believe that is 0.35. From the median to the maximum, 5.3, that's going to be 2.53. Am I right on the distance there? I'm trying to, no? 1.65? No. From median to max. 3.55. Thank you. What is it from the median to quartile 1? Because apparently my math's not working. I think it's 0.4. 0.4. So that's a bigger difference. What's the distance? Actually, no, this is closer here. What's the difference between the minimum and the median? That's the 1.65. So you can kind of, I understand making the arguments about saying, hey, well, this is actually closer. Well, this is closer here. This is closer here. But the truth of the matter is that the values further away from the median, from the average, are going to have more of an effect. So that second little box there is what does that. So that would tell me that it's skewed to the right. Again, you might have your median slightly closer to one quartile or the other, but it's the outliers, it's the data far away, it's the first and last quartile. Those are the guys that are going to have the most pull on your data. So after that data was picked up, 3 more students visited the nurse. Temperatures 96.7, 98.4, 99.2. Were any of those students outliers? Yes? Which ones? 96.7 was an outlier? Was the 98.4? No. How do you know the 96.7 was an outlier? Okay, 96.725 for the lower fence. So it's just barely outside of that fence. And that's really all the justification that you would need for this. You would need to tell me where your fences are. And then you would say, 96.7 is an outlier, it's outside my fence. Oh, no. Call it a fence. Call it a fence. You're good. No worries about that. Okay? That's one of those standard probability and statistics terms. Unless you're talking about building fences, and then everything gets weird. I don't know. All right, for the second one, there have been a lot of AP free response questions that have given you something like this. And then they ask you various questions. So if we're looking at our choices here, which role involved the youngest person and what's the age? The passenger? What age? Less than 1 year? I would go with that. Can you be 0 years old? Yeah, Yes. For those first 364 days of the year after they're born, they're less than a year old. It's okay. That's fine. That's getting close down there, because let's kind of think about that. Are you going to have somebody that old driving? Are they going to be riding a bike? Likelihood. What about a pedestrian on the side of the street? Yeah, when you've got your little babies, they're most likely to be moved around either in a baby stroller or hopefully in a child seat in the back seat of the car. Let's hope that's the way it goes. Which role had the lowest median age? Lowest median. Passenger, again, good. What would you guesstimate that to be? I'd say 21-ish works just fine. Which role had the smallest range of ages? The cyclists. Now, what would you say that range would be? Okay. About 40? I would definitely go with that. And if you think about it, I think that this graph is actually very misleading, because I know of many people significantly older who ride bikes. It's kind of amazing what they do. It definitely does not stop before you hit 60. And so I know if they're riding their bikes as they're older, they're probably also going to get in car accidents or bike accidents as they get older. Just, I don't want to take that amazing accomplishment away from people. So who had the largest interquartile range? Largest IQR? Pedestrians. What is it? What is the range? What is the IQR for pedestrians? Guesstimate. See, if you didn't say 44, I'm sorry, you're wrong. You're all wrong. You're all going to fail. It's just the way it is. No, 45 is perfectly acceptable here. The only reason why we have these exact values is because we have the values that were used to make that. So these better be exact. Yes, ma'am. No. The interquartile range, I know, I'm sorry if that came across too harsh. The interquartile range itself is that value. You can say the interquartile range goes from and to, but if I ask you for the range, that is a number. Okay. Which role generally involves the oldest folks? Generally involves the oldest folks. Because we're pretty much, what do you think? How many of you say cyclists? All right, so we're clear on that. It's not the cyclists. I would assume that we're probably broken down between driver, pedestrian, and passenger. Am I correct? Anybody want to eliminate one of those? You should be able to eliminate passengers. Because if we look, this middle line here in each of them means 50% of the data lies above it. So this upper quartile here is still below the median on this one. And it's just above the median on this one. So although they might reach approximately the same oldest person, generally, passengers are out. So now we're going to come down and look at drivers versus pedestrians. Generally speaking. Generally speaking does not mean the oldest person. Yeah. Mm-hmm. Almost. Only problem is this quartile does actually dip below that one. So making the argument towards the whole interquartile range doesn't necessarily fit, because we don't know if that's just one person here and then everybody else is tightly clustered up in here. We don't know how that's distributed. You could actually break it down by all sorts of pieces. It's okay. Okay, you're also going along where Eden was, but you want to be a little bit more specific for that. You want to say the top 25% in the pedestrians is definitely older, generally speaking, than the top 25% here, that your range starts higher. You can also say that the top 50% of the data for pedestrians starts at an older age than the top 50% of the drivers. Okay, but in both cases, the median for pedestrians is higher than the median for the drivers, and quartile 3 for the pedestrians is higher than quartile 3 for the drivers. So that whole general distribution is slightly higher. So even though a driver might have the older person out of those two groups, if we're looking at the 50% and the 25%, they're both starting at a higher rate for the pedestrian rather than for the driver. Yes. Exactly. If I wanted to know who had the oldest, what did they say? They said which role involved the youngest person. I would say which role involved the oldest person. That's the difference between looking at a singular and a plural. Okay, looking at the group versus one. Exactly. And you want to compare things like medians to medians, quartile 3s to quartile 3s. And if you have both of those higher for one group than the other, that kind of leads you towards your answer, because we don't know how within each of those groups our data is distributed. Your data could be extremely heavily smooshed right here. Your data could be heavily smooshed right here. We don't know. That's the bad part about a box and whisker, is there's not much about the individual data points that we know. We only understand those 5-number summaries and whether or not we have outliers. Okay? All right. Have all my cell phones in the back of the room? Clear your desks. We're going to take our quiz. Just not funny. Okay. So today what we're doing is we're moving into Chapter 5. The previous chapters we've been describing distributions. So in Chapter 2 we were talking about categorical displays. 3 and 4 we were talking about quantitative. And we were focusing on this idea of skewed versus symmetric. Because with skewed we use median and interquartile range. Whereas with symmetric we use standard deviation and mean. But what does standard deviation actually mean? Yeah, that's not even where I was going for, but hey, it worked out. Why not? So the standard deviation basically becomes for us a ruler by which we measure everything else within the group. Okay, it's a very powerful tool. Basically what it does is it allows us to compare one element against a whole group to see if there is a difference, how does it compare to the whole group, because we like to compare. Standard deviation is also a measurement of how the entire group varies, but it's done in a very specific way. Okay? What it does when we do a standard deviation is it allows us to kind of, sometimes we can actually, you know that saying you can't compare apples to oranges? Using standard deviation, you can. It allows you to compare completely separate groups. It allows you to compare within groups. Standard deviation is basically how we look at data. And the way standard deviation is calculated, so we've got our crazy formula, which you're probably never going to use because your calculator does it for you. But standard deviation is found by looking at the average from a set of data. And then from every single piece in your data set, finding the difference between that value and the average. Then it squares that, makes everything positive, divides it by an adjusted total of the group, so either by n or n minus 1, depending upon if we're talking about population or sample. Then it takes the square root of all of that. So it's a measurement of differences. We like to talk about z-scores in this class because I want to compare apples to oranges. And basically, a z-score is going to allow us to compare all elements across all groups. And the z-score is just a measurement of how many standard deviations away are you. So if I use that standard deviation of a ruler, how many of those away from the average are you? So this is a formula that you will be using quite a bit. And it says that our z-score, or our standardized score, is equal to our particular value minus the mean divided by the standard deviation. I like to say it observed minus expected, because you expect the average, divided by the standard deviation. And this is something that is going to come up in pretty much every single unit from here on out. We're going to be using that formula. It is a standardized value because we're dividing by the standard deviation. This top portion has the units of your original data. The bottom portion has the units of the original data. So when you divide, the units go away. And so standard deviation actually has no units. It is just going to be a number. And it allows us to compare across multiple groups that might not have anything to do with each other. We like being able to do that because, well, sometimes I want to say, who's the better student? And I want to look at your math score compared to somebody else's English score. How can I do that? And it's by standardizing them, getting them a standard ruler by which we'll measure them. Basically, all z-scores are doing are measuring your distance from your observed to your expected in terms of those standard deviations. That's all that is. Okay. Now, you got to be careful because a negative, people oftentimes think a negative anything is bad. Negative means bad. Positive means good. But it doesn't. A negative z-score just means it's less than the median or less than the average, the mean. A positive z-score means it's above the average. That's all they're talking about. If we're running a race, how do we measure running a race? How fast? How do I measure how fast? Stopwatch, so I measure it in seconds, in time. If I'm running a race, do I want to be faster than average or slower than average? And how does faster relate in times? Do you want that to be a higher time or a lower time? See how you've got with that? It's all about the context, what's better and what's worse. So you actually want to have a negative z-score if you're running a race. If I'm taking a test and I want to be better than average, do I want a higher score or a lower score? Higher. Will my z-score be positive or negative? Positive. See? It's all about context. Now, also what happens with data is we do a lot of shifting. So how might that work? Well, adding or subtracting. For example, okay, this is not, I'm not doing this, but let's say I decided to be really, really nice and add everybody 10 points to your quiz you just took. She was like, what? Are you going to do that? No, I'm not doing that. But let's say I did for the sake of discussion. I'm going to take your distribution of your scores. Every single individual gets 10 added to it. What's that going to do to my distribution? It's going to change it how? It's going to shift it over. Correct? What does it do to the minimum value? Shifts it over. What does it do to the mean value? Shifts it over. The maximum? Shifts it over. If I went from here to here, what is that doing to my spread? It keeps it exactly the same. I did not change how far out I was spread. So adding or subtracting an amount to every single value is going to move every single position. It is not going to change any measure of spread. So it's not going to change your range. The difference between the highest and the lowest is still going to be the same. It's not going to change my standard deviation because I'm not changing the general spread of my data. So here's an example. We've got here the weights of a whole bunch of different men. And here is their weight, generally speaking. There's their weight in kilograms above recommended weight. So what they said is the recommended weight is 74 kilograms, whatever that works out to be. Recommended weight is 74 kilograms. So we can see here, that's about right here. Now I want to look at the difference. So that means I'm going to take 50 minus 74, 100 minus 74, 150 minus 74. All I did was shift my graph over. Even on my box plots, Did my spread change at all? No. But the center of the two distributions, so if I were to talk here, that's 50, 60, let's say probably about 70, it's going to be skewed that way, so maybe 75 to be my average. And my average over here, it's also going to be 0, or 1, because we're subtracting 74. But it's not going to do anything to the interquartile ranges. The interquartile ranges are going to be exactly the same. So far, so good? Adding something to everything changes position. Now, if I were to multiply by something, if I were to scale your data, it's like, okay, I'm going to take your quiz, and I'm going to now times your scores by 2 and have your quiz out of 100 instead of out of 50. Do you like that idea? Who does that help the most? Good scores. Because good scores see a greater increase versus the lower scores. Which is why they oftentimes talk to teachers. Math teachers get this, other teachers don't. You don't just say, oh, okay, so your test was originally out of 100. Okay, let's take it out of 90 instead. Because that's going to benefit the people at the very top. The people that were over a 90, they're going to be way over 100. For the people at the bottom, they're not going to change very much. Because if you think about it, what's 0 times 2? 0. So that 0 is locked in place. Everything else is going to stretch out accordingly. Does that make sense? Okay. So when we're talking about rescaling data is going to move position, and it is also going to change your standard deviation, your interquartile range, your range. But it affects it in different ways than you might expect. And we're going to come back to that in a couple units. So here is talking about rescaling from kilograms to pounds. Do you see how it took my data? All of my frequencies are still the same here. But it's taken my data and it's spread it out. Did I actually change a person? No, but the way that we distribute it has changed. So the center here is going to change from where we said it was about 75. And if I were to look at the center over here, let's say about 170, maybe. Which if I'm mooging, it's like kind of like bougie and moving at the same time. Mooging. If I multiply by 2.2, that's what you would expect to occur. The range is not quite so straightforward all the time, but the range is also going to have a multiplier applied to it. But I don't want to tell you that it's just, hey, multiply the range by 2.2, because it's not always the case. All right, so back to the z-scores. When we're talking about z-scores, its purpose is to shift the data so that the average is 0, because it's a nice place to start. And rescale it. So your standard deviation, instead of some wonky number, is going to be 1. And it allows me to compare across groups. So standardizing, when we move to z-scores, it doesn't change the shape of the distribution. It just changes what we look at for the center now being 0 and the spread now being 1. Because that's what standardizing does. We get to a nice standard unit of measurement. And the way that we denote this is with the normal model. You guys have heard of the normal model before, right? Maybe in Algebra 1, maybe Algebra 2. They've changed the curriculum, so who knows anymore. But you want to be awake for this. Okay? So the normal model is a way that we can describe shape, center, and spread. And when you are doing this on your paper, you will always write, and I'm not kidding, always, you will write N for shape, parenthesis, mu equals something, sigma equals something. You will always write that, even if we're talking about samples. That is going to be the standard notation for AP grading. And hey, if I'm describing the distribution, I just included shape, center, spread. Okay? But if we're standardizing it, because we've calculated the z-scores by subtracting the average and dividing by the standard deviation, my standardized normal model will become N mu equals 0, sigma equals 1. Okay, that's very, very important. Z-scores, if we're talking about Z-scores, mean is 0, standard deviation is 1, period. Okay? But not everything can be set into the normal model. There's a whole lot out there that can be, but there's even more that can't. I mean, we talk about incomes, heavily skewed data, bimodal data. That does not fit with the normal model. But when it does fit with the normal model, we are extremely happy. We get something called the empirical rule. So like the hoity-toities will call it the empirical rule. I feel so like empirical. I'm king. I'm man of them all, person of them all. But the empirical rule is also known as the 68, 95, 99.7 rule. It's quite straightforward. What it says is in a normal model, look at me, I'm standing on the average. If I reach out 1 standard deviation in either direction, I should capture 68% of the data. Or if I stretch out just a little bit further, and now I go to 2 standard deviations, you want to take a guess what I'm going to grab? 95% of the data, which is a really big group. It leaves me only 5% on the outside. Hey, that 5% that I've mentioned a couple of times. 2 standard deviations is where things start to get a little interesting. 3 standard deviations is going to grab how much? 99 point. See? Don't you love that rule? It's in the words. 3 standard deviations take almost everything. So if you calculate a z-score and it's more than 3, that's not just crazy. That's smack your grandma crazy. Please don't go smacking your grandma. But it's like one of those, whoa! If you're not careful, you'll smack your grandma. And this is what the normal distribution looks like. Hey, it's a bell curve. BT dubs, never ask your teacher for a bell curve. Bell curve's bad. Bell curves mean you have exactly as many A's as you have F's. B's as D's. And most everybody gets C's. You're like, well, I would be the A, so bell curve is awesome. No, don't ever ask for a bell curve. But when we do this, we always have to label our normal curve with our mean, our standard deviations as we go out, and you can either write the 3 percentages or you can actually break them up into their pieces, which we will be talking about. So, why the heck are we doing this standardization stuff? Anybody in here in track and field? Cross country? No? You all boring? Lazy? No, I'm in other stuff. You can see how each performance relates to the average. So, here we have a track and field competition. Track and field is the idea of combining separate events into one. And your overall performance for all of those tells you how you scored in general. And the way that you do that is you start with the idea that every event has an accepted average, like what the average speed or distance or whatever it is for participants is going to be, and they have a standard deviation calculated. And what you're going to do is you're going to look at how your score compares to each of these. So what I want you guys to do, this is in your notes, I want you for each of these, this one, 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 I want you to calculate their z-scores. So when you calculate their z-score, what you're going to do is you're going to take observed minus expected divided by standard deviation. So it would be 10.1 minus 10 divided by 0.2. That is going to give you your z-score. And there might be something you want to notice before you go in. And look at your data real quick. Anybody see something irritating? What do you see? The mean's not right? This is not the mean of these 3 competitors. This is the overall mean. These are the people that I think are in the top 3 positions. Say it again for me. Long jump has different units. What is this measured in? Feet. Feet and inches. That's feet. That's inches. So you might want to start by changing those 2 numbers to feet. Go for it. You should have done, come on, work. I worked hard to get this animation. 27.25 and 0.5, converting those into feet. When I go through this, your first step is to find all of your z-scores. So here are my z-scores. Going down each column, I had 0.5, negative 0.5, 1.5, 2, 0, 1, 0, 2, 2.5. Sound about right? Okay. In order to figure out who placed first, second, and third, we need to put these together. But we need to be careful. Do I want positive or negative z-scores for the 100-meter dash? Negative. I want to be faster than everybody. For shot put, positive, and for long jump, positive. So in order to combine these and to figure out who did better, I actually am going to need to change that 100-meter dash to things that are good. So what would I change this to? Negative, positive, and negative. And so when I do that, that's what we get. So now I can add up these guys to see who's above average, who's below average, where are we? So who would you say finished in first place? B? Okay, second place. C or A? Because A is going to give me 1.5. C is going to give me 2. So then it's going to be C and then A. Because if I just add across. So do you see how I can compare things that are even in completely different groups? If I just want to make sure that I think of my z-scores as which one is better and keep that consistent, you're okay. Now, the second piece says, who turned in the most remarkable performance at the competition? This is not saying overall who won. We already did that one. This is saying who did something up there that would make you go, oh my gosh! Yes. C in the long jump. Absolutely. That is more than 2 standard deviations away from average. That's something that you would look at that and go, oh, wow, that's amazing. So C in the long jump is the guy that had the z-score that was furthest from the average. Now, it doesn't necessarily even have to be a positive. It could be a negative. There are people where you watch the Olympics and some countries put together a team and you doesn't necessarily mean that you're special. It means that you're one of the 5 people that tried out for the team. And yeah, you finish the race 2 minutes behind everybody else. That's pretty remarkable as well. Or somebody who got injured as they were doing the full jump. The vault. No, whatever that is. I don't know. You guys get what I mean. So, yes, pole vault. Competitor C had the crazy one. So, IQ is a very common method that we're going to be looking at here. How does an IQ work out? IQ test is a normal distribution. And in an IQ test, you're basically looking at the mean to be 100, the standard deviation to be 16. So I want you guys to draw and answer. Answer these questions. Our goal over today and tomorrow is going to be able to get as much practice in as humanly possible. Because there's like a lot of little different things that you can do to look at these problems. Right, Eden? She's like, yes. But it's not that bad, was it? Not horrible. Poor Eden's going to be out all next week. And the next week, probably. That just stinks. Let me show you how it's done. So this is the general setup for the normal curve. What am I talking about? What's my context? IQ scores. So I'm going to title this IQ scores. That's what's going to be along this axis here. What is your average IQ score? 100. So that goes in the middle. What was my standard deviation? 16. So what goes here? 116. What goes here? 132. And then here? 148. To the left. What goes here? 84. Back it up. One more time. 68. Back it up. 52. We also have the idea that in our normal curve, we have 68% is within that first window. So if that's 68%, what's in this little piece here? 34. And that means this piece also has 34. Now, if I step out one more standard deviation further, what percent is that? 95. So what is the difference between 68 and 95? Math. One more time. 27. Divide that by 2 because that's going to go here. One more time. 13.5. These numbers are going to become very familiar to you. And then that means the last one is going to be 99.7. So I'm going to subtract 99.7 minus 95. Divide by 2. 2.35. And how much is an entire curve? 100. So I've got 0.3 left. What goes to 3 standard deviations and beyond all the way out? What's left? 0.15. So this then makes answering questions really easy. I don't care if you put these 3 numbers or if you just always use those numbers. I typically just go with these numbers because I know that I use those more than anything. So in what interval would you expect the central 95% of IQ scores to be? And we will finish this up next class. Please be sure you watch the video. It will be posted by the end of the day today.